And now the fun begins, finding the pH of a weak acid. First of all, let's be really clear. Strength and concentration are not the same thing. I hope that is clear for everyone at this point. Whether an acid is strong or weak is an indication of how dissociated it is in solution. The concentration refers to how many hydrogen ions are in solution. So if I want to find the pH of a weak acid, I need to know how many hydrogen ions there are in concentration. But because the concentration of the acid does not equal the concentration of the hydrogen ions, because our weak acids are not fully dissociated, we have to find where the position of equilibrium lies in order to figure out what the concentration of hydrogen ions is. So let's break that down, and I'm going to go right back to basics here. So let's take ethanoic acid. Dissolve it in water, and we've seen this before. We're going to form ethanoate ions and our oxonium ions. Right, there's a reason why I'm not simplifying it straight out, so bear with me. To find where the position of equilibrium lies, I can write the equilibrium expression. So the equilibrium constant, Kc, is equal to the concentration of the products divided by the concentration of the reactants. Okay, if the position of the equilibrium lies to the right, then that would indicate that I have a higher concentration of products than reactants, and the value is going to be greater than 1. If, as in the case of weak acids, we know that the position of equilibrium lies to the left, then the concentration of reactants is going to be higher than the concentration of the products, and Kc is going to be less than 1. So just putting some kind of perspective in that. So for this particular reaction, Kc is going to equal concentration of the products. Remember, square brackets indicate concentration, and to be correct, we should include state symbols always. Although when we're doing actual calculations, we tend to get a little bit lazy with that. But if you're asked to write an expression, you need to make sure you've got the state symbols in. Concentration of the reactants. So that's the ethanoic acid and water. Now, water is so far in excess that it is effectively constant. So we can rewrite even this expression. So let's remove water by multiplying it out, move it from the right-hand side of the expression. So Kc times water, so we've got both our constants on the left-hand side, is going to equal COO minus H3O plus over our ethanoic acid. Now, if you have watched the video on the ionic product of water, hopefully you're going to be able to see where I'm going at this point. Where I have got one constant multiplied by another constant, I have the exciting opportunity to produce a third, and we're going to call this constant Ka. Ka is known as the acidity constant, or more commonly at A level as the acid dissociation constant. Dissociation, can't spell today. There we go. Constant. So that means that for this particular reaction, Ka equals the concentration of the ethanoate ions, square brackets for concentration, multiplied by H3O plus divided by ethanoic acid, Q. Now I hope you can see why I didn't simplify straight out. So let's generalize this. In general, where we have got our acid as HA, and we can simplify it to dissociate to form H plus ions and A minus, then we can say that Ka is equal to the hydrogen ion concentration. Gosh, God, squeeze my AQ in there. The anion concentration divided by the concentration of the undissociated acid. Okay, this expression is hugely important for the rest of this topic. Pretty much every single calculation we come across, whether we're looking at acids, bases, buffers, indicators, we're going to come back to some form of this expression. So please take some time to go back through this video, make yourself some notes, really get your head around what we're saying here. Ka values are influenced by temperature but not by the concentration of the acid. So it's a really accurate measure of the extent of dissociation. And I've given you a few examples here. We can see that as we move up my table, the Ka values are increasing. Chloric acid is a very strong acid, and as a result, we can see that it has a high degree of dissociation, 1.1 times 10 to the minus 2. Phenol, on the other hand, is a very, very weak acid. It has a Ka value of 1 times 10 to the minus 10, which implies that the position of equilibrium lies very, very strongly to the left, and it's hardly dissociated at all. Once again, because we've got a really big range in Ka values, it makes sense to represent them on a logarithmic scale. So just like with hydrogen ion concentration and pH, we can work with pKa values. pKa equals minus the log 10, again, of the Ka value. So it's a logarithmic scale, and you can see here that we have the opposite trend. The stronger the acid, the lower the pKa value. I want to work through this question here very, very slowly in a lot of detail so that you can get your head around these relationships that we've been talking about, the Ka, the acidity constant, pH concentrations, and position of equilibrium in terms of a weak acid. So calculate Ka for a weak acid given that the concentration is 0.1 mol per decimeter cubed and the pH of this solution is 5.10. So we don't know what the acid is, but that doesn't actually matter because we have all the information. So let's start with our basic expression. HA dissociates to form hydrogen ions and the anion AQ. What do we know? Well, initially we know the concentration of the weak acid. So I'm going to write that up here. So initially the concentration of the weak acid is 0.100 mol per decimeter cubed. What's happened at equilibrium? Well, once we dissolve this acid in water, an equilibrium is set up, and even though it's a weak acid, some of HA will have dissociated, a very small amount, but some of it will dissociated. How do we figure out how much that is? Well, I know that the pH of the solution is 5.10. So pH equals minus the log of the hydrogen ion concentration. So if I know one, I know the other. So my hydrogen ion concentration at equilibrium is going to be 10 to the minus pH. So that's 10 to the minus 5.1. And when you plug that into your calculator, it comes out at 7.94 times 10 to the minus 6 mole per decimeter cubed. This is a really small number, which is what we would expect. Very few of our weak acid molecules, HA, are actually dissociating. So, if I go back up here at equilibrium, it's my shorthand for equilibrium, I know that the hydrogen ion concentration is 7.94 times 10 to the minus 6. Now, let me change colour, make it a little bit clearer. Looking at my expression here, the ratio of HA, acid, to hydrogen ion to anion is 1 to 1. So I know that if I have produced, first of all, if I've got 7.94 times 10 to the minus 6 mole per decimeter cubed of hydrogen ions, I must have the same number of the anion. So I now know the concentration here, 7.94 times 10 to the minus 6. I can work in concentrations here because the volume is constant. In terms of the acid, well, at equilibrium, again, it's a 1-to-1 ratio, molar ratio. So we can say that 0.100 minus 7.94 times 10 to the minus 6, so it's a 1-to-1 ratio, tells us how many of the acid, the concentration of the acid molecules that's changed. And that turns out to be 0.9999206. Now, I'm putting that full number in there for a reason. The difference between the concentration, the number of moles, whichever you want to work in, of acid molecules at equilibrium compared to initially, the difference is absolutely minuscule, which is what we'd expect. It's a weak acid. Very few of our acid molecules are dissociating, which means that when we come to do our calculations to find the pH or the Ka of weak acids, we can make two assumptions. And these are absolutely vital. Our first assumption is that the hydrogen ion concentration at equilibrium always equals the anion concentration. We can see that here. That makes complete and utter sense because our acid molecules always dissociate in a ratio of 1 to 1. So that is assumption number 1. Assumption number 2 is that because we are working with weak acids, to all intents and purposes, the concentration of the acid initially and at equilibrium is unchanged. So assumption number 2 is that HA concentration remains unchanged. This makes doing calculations very, very straightforward, because what we can now do is we can go to our expression for Ka. So Ka equals products over reactants. I'm going to simplify here, take out the state symbols, which is just pure laziness, but it also simplifies this very nicely. So the hydrogen ion concentration is 7.94 times 10 to the minus 6. The anion concentration is also 7.94 times 10 to the minus 6. And our second assumption is that the concentration of the acid, to all intents and purposes, remains unchanged. When you plug that into your calculator, it comes out to be 6.30 times 10 to the minus 10 mole per decimeter cubed. This is an exceptionally weak acid to have such a low Ka, and that is reflected in the fact that despite the concentration being 0.1, we have, yeah, I've got that right, so mind blank there. Despite the concentration of the acid being 0.1 mole per decimeter cubed, the pH is only 5.1, so it is a very, very weak acid. finding the pH of a weak acid, again, we need to go back to our expression for our acidity constant. We are always, always, always going to go back to this expression. And it doesn't matter what the acid is. So I'm not going to write it out for ethanoic acid, I'm just going to write out the general one. Remember, if the actual question asks you to write out the expression to put in your state symbols, but since I'm just doing a calculation, I'm going to be very, very lazy here. Now, the key to all calculations in chemistry is to have a method and stick to it. So this is my method, and as far as I'm concerned, it is pretty much foolproof. I use the expression and the question to pull together all the information that I need. So what do I know? I know that the Ka is 1.7 times 10 to the minus 5 mole per decimeter cubed. Our assumption is that at equilibrium, because this is a weak acid, the initial concentration of the acid remains unchanged. So that is 0.100 mole per decimeter cubed. I'm trying to find the pH. I know that pH equals minus the log of the hydrogen ion concentration. And I also know that the assumption is that our acids dissociate on a one-to-one basis. So the hydrogen ion concentration equals the anion concentration. I now have everything I need to complete this calculation. So Ka is going to equal H plus squared, because hydrogen ion concentration equals the anion concentration, divided by the concentration of the acid. Rearranging that, it becomes hydrogen ion concentration squared, we want to get that on its own, is equal to the Ka times the concentration of the undissociated acid. So that tells me that, let's go back over here, hydrogen ion concentration squared is going to equal 1.7 times 10 to the minus 5 multiplied by concentration of the acid, which was 0.100. So that's 1.7 times 10 to the minus 6. If I square root that, so the hydrogen ion concentration, as I said to start with, I'm going to go very slowly through this. So 1.7 times 10 to the minus 6. If I square root that, I'll find the hydrogen ion concentration, and that comes out to be 0.00130 moles per decimeter cubed. If I know the hydrogen ion concentration, I can figure out the pH, because pH equals minus the log of the hydrogen ion concentration, 0.0130, and that comes out to be 2.88. If this has been useful, hit the subscribe button, the effortless way to support your studies, and by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.